Okay, so we're going to take a look at hyperbolas in this section, and once again, I'm going to strongly recommend that you print out the 7.5 PowerPoint posted on the portal so you can take notes and read the examples more clearly than what's posted on this slideshow. As we construct our hyperbola, we need to have 2 points, F1 and F2, that are equidistant from a set point, and our hyperbola is created by finding all of the points that are equidistant from the directrix. In order for us to graph this hyperbola, we are going to find some values from the equation, similar to the ellipse and the parabola, not so similar to the circle, but we need the A and the B from the denominator to help us figure out how wide and then how long the parabola is, and we will be connecting the corners of that box to help us graph the outside, the actual parabola itself. Connecting those corners helps us create asymptotes or guidelines for the shape of the parabola itself. In this slide, we can't see anything of what was originally on the slide, so our basic equation for the hyperbola is x squared over a squared minus y squared over b squared equals 1. This means, because the x is in front, that we would have our parabola opening out along the x-axis. If we had a y squared in front, we would have the parabola opening up and down. In order to help us find some of the points for the foci, we need to figure out the value of C to get those focus points, and that's going to come from the Pythagorean theorem. Unlike what we did with the ellipse, this one truly is the Pythagorean theorem, and we would be adding and subtracting that from the actual center of the hyperbola. The slope of the asymptotes is coming from the values of A and B. If the hyperbola is centered at the origin, the equation of our asymptote would literally be however, if we shift the hyperbola up, down, left, or right, that linear equation is going to move as well. And so then all we would have would be the slope that we'd be able to get from the original equation of our hyperbola. So in this problem, we want to find the graph for y squared over 25 minus x squared over 4 equals 1. So since the y squared is first, this hyperbola is going to open up and down. We would have, quote-unquote, the a value is equal to the square root of 25, which equals 5. And then our b value is the square root of 4, which equals 2. So if I go from the center at the origin, I'm going to go up 5, and I'm going to go down 5, and then I'm going to go over 2, and over 2, and this is helping me to make a box. And this box that I'm making here, I'm going to use it to connect corner to corner so that I can find the asymptotes of my hyperbola. And you might be able to do this a little better than I can because your lines will be a little neater. Now, the vertex of my parabola is going to, oh wait, it's opening up and down. So my vertex is going to touch here at 5 and negative 5. But I still need to find the focus, or the foci. So that involves finding my C value. And so I'm going to take 25 plus 4, which doesn't give me a really nice square root value. So the square root of 29, it's a little more than 5, it's not quite 6, so I'm going to turn that red so that we can see that my focus is, let's see if I can make a mark on here, in between 5 and 6. You'll do a little better than I did. That's C. And then when I go to graph this, I'm going from the vertex and I'm using my asymptotes as a guideline. Using my asymptotes as a guideline. There we go. And to find the equations of the asymptotes, I would have y equals plus or minus, let's see, the slope on that, I'm going up 5 over 2 x, which happens to be a over b instead of b over a, which would be because our graph is opening up instead of opening sideways, the way that it was demonstrated in the original formula having the x squared first. So in our hyperbolas here, this is showing the difference between having a horizontal, which means our graph opens sideways, and a vertical, opening up and down. Again, I always consider a to be the larger number. This doesn't quite say it that way, but it's really the same idea that you have something that's squared underneath both of them, and your center, h always goes with x, k always goes with y, and again we need to be able to find c. Okay, so in this graph, if you can't tell, we have a 25 underneath here. So let's find the center first. Oh wait, and I should call that center instead of C. Our center is at 2, 0, so I'm going to move the graph over 2. And then my A value is the square root of 9, which equals 3. And my B value is the square root of 25, which equals 5. So from the point, on the x-axis, from the point of 2, I'm going over 3, and over 3, and then back to that center point at 2, 0, I'm going up and down 5 to help form my box. Okay, and now I'm going to use that box to help me get my asymptotes, which are my guidelines. And as I look at my original equation, I have an x squared, so this is opening horizontal, And the center, or the vertex, sorry, is going to be on the x-axis. And I can use my asymptotes as guidelines. I also need to find the c value, which is going to equal 9 plus 25. I think that gives me 34, plus or minus. So to find the foci, we have 2 plus the square root of 34, comma 0, and we have 2 minus the square root of 34, comma 0, and the square root of 34 is almost 6. So 2 plus 6 would give us almost 8, almost but not quite, and then 2 minus 6 would give us negative, not quite, -4. And so those two values in red there are approximately where the foci would be. And I can find the slope of the asymptotes. So looking at my rectangle, I can see that we went up 5 and over 3. But I certainly don't have y equals plus or minus 5/3 x, since we had that shift over 2 units to the right. Now for this fun equation, I need to complete the square on my x's and y's. So let's see what we can come up with. Okay, so when I work on completing the square, I have my 9y squared, and then I need to focus on the x squared minus 6x. I'm going to factor out a -1, which gives me x squared plus 6x. I'm going to divide by 2, which gives me 3. 3 squared is 9. So that equals 10. Now, it looks like I added 9 right here, but I have a -1. So 9 times -1 means I really subtracted 9 from both sides. So I have 9y squared minus x, and then this was a negative that I had in there, and my 6 divided by 2 tells me that I have a 3 that's being squared equals 1. But I'm not supposed to have a coefficient in front of the y squared. So multiplying by 9 is the same thing as dividing by 1/9, which is not how we normally work with this, but I need a divided by to put this in the form for a hyperbola. Minus x minus 3 squared, technically over 1, equals 1. So now my a value, if I take the square root of 1/9, is 1/3. My b value, if I take the square root of 1, is 1. So if oh, and I need to find my center. Okay, so my center, my x value is at 3, my y value is at 0. So centered at 3, 0, I am going up by 1/3. It's going to be a little tricky to put on here. And down by 1/3, and then I'm going over by 1, and that's the box that I'm going to try to make into my asymptotes. So supposedly I'm going up 1 and over 3. So I can actually make my asymptotes from that. So up 1 over 3 from my center. Up 1 over 3. Up 1 over 3. Hope I got that right. So that's an asymptote. Alright, and then if I go the negative way, okay, and I need to find my focus points. So I would take the square root of 1/9 plus 1, which is the square root of 1 and 1/9. And 1 and 1/9 would also give me the square root of 10/9, or the square root of 10 over 3, plus or minus. And so from my center point, I would have 3 plus 10, square root of 10 over 3, comma 0, and I would have 3 minus the square root of 10 over 3, comma 0. So I'm going to say that's almost 1 and almost 1 out there. Oh, whoops, wrong direction. This is going up and down, not side to side. The reason I know it's going up and down is because it's a y squared. And so that means I need to make, on that box, I need to make a really wide hyperbola. So the topic of eccentricity talks about like how squished or how elongated a hyperbola is. We have the same idea with an ellipse as well, whether we have a really round ellipse or whether we have a long and narrow ellipse. And the formula to find eccentricity for both of them is really the value of c divided by a. It's just that finding c is different whether you're talking about an ellipse or a hyperbola. And there is no eccentricity for a parabola because that distance from the focus to the directrix always equals 1. So parabolas are not eccentric, but the other two can be. So if we try to find how curvy this particular conic section is, we have to find c, which comes out by taking a squared plus b squared, and thankfully they finally gave us some nice numbers to work with. Because when you add 144 and 25, you get the square root of 169, and that gives us 13. So E would be 13 over A, and A in this case is 12. So this would be a not very curvy hyperbola, because 13 over 12 is pretty close to 1. If we had something like 5 over 12, it would be considerably curvier, but this, not so curvy. Amazingly enough, the hyperbola also has a latus rectum, and the formula to find it is not that difficult. The length of the latus rectum is 2b squared divided by a, and we can find those values very easily from our original equation. So a here is 12, b squared is already given. So if we plug that in to our formula for this particular parabola or hyperbola, we would say 2 times 25 over 12, which looks like 50 over 12. And if we reduce that down, let's see, 2 goes into both of them, so that'd be 25 over 6. I don't think we can do much with that. And that is the length that goes through the focus that touches the actual hyperbola. And there happens to be another one that would be over here. It would be the exact same length. It's just not being shown.